So the first style that came out was the round, commonly called the round rail. So the round rail has a round shaft that would be on it, and then you would, for instance, if this were the bearing block, you would have the bearing that went, oh, let's see if I can draw this here. Yeah, okay. So here's going to be the bearing. The bearing surface goes around here. Yeah, and it'd be something like this. So that's kind of what would happen. And then the balls would actually be in here. And there might be, in this case, there might be a few rows. And these rows would be, there'd be row here, and then there'd be a return. And this is the case with all linear bearings. You pretty much have to have some sort of loading position. And then you have unloaded, which is the return. So rotary bearings have this to a lesser extent, but a linear bearing, it pretty much, as this moves along the travel here, this bearing would roll along and it would finally get shoved into the loading zone. And then it would be one of the rollers that rolled along in the loading zone along here. It'd be, you know, as it went along, and finally it would pop out. And there's a little bit of pop outness to the bearing actually as it pops out of the loading zone and goes into the return tube until finally it's shoved back in there. And whenever you hear bearings, let me see if I have some that are, yeah. I don't know if you can hear the sound of this bearing. Here's a different kind of bearing, but let's see if you can hear this sound. This bearing has a sound to it. And you're just like, what is the sound? Most of the sound in a bearing, in a linear bearing, is from the balls touching each other. Oops. And clanking back and forth. But a lot of the feel that you'll feel is this entering and exiting the loading zone. Because they physically, the way any linear bearing works, let's just talk about this for a minute before we get to the types. The way when you have what I've drawn here, I have a round rail, I'm going to exaggerate it, and then I had a little, I'm going to exaggerate this a little bit, the ball bearing was here. And the force would be along this axis. It pretty much has to be on this one. That's the only way you can transmit force. So what you have, this would be called point contact in the bearing world. This is kind of bad. On one hand, this is point contact to point contact. If we had just a bearing, let's say you had a flat surface and you had a bearing rolling along a flat surface, then you would have in this area here, right there, you would still have point contact, but it would be to at least a line of flat surface. And what you want to always think about is this bearing ball gets it gets squashed is the way to think about it. The way that you actually make this work is it has to go under load, and whenever you put this round, let me exaggerate it here a little bit. Whenever you put this ball, I'm going to exaggerate this now, round, at some point down here, it has to flatten out as it carries load. I mean, you guys know this with any ball that you bounce or a tire, anything that's round, when it rolls along the surface at the bottom, it goes flat on the bottom of your tire. There's a section of it, maybe called the contact patch, and it might be this long, might be longer if you air down a little bit, and real short if it's a really high pressure. but there's a period where it conforms to the flat surface, not the other way around. It's the flexible thing, and the other surface is the non-flexible thing. And so the flexible thing, being the ball bearing, will conform at some point to the flat surface. And every time it changes shape, two things happen. One is it takes energy to change shape, but the other thing is that you have non-similar velocities. And so you start to if you point contact to point contact, like right here, as that thing rolls along the length of travel, as it rolls along this, there's almost nothing touching because it's round to round. And so it's just, it's one of those things where if you ever drop a bearing on the ground and they're boing, 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 and it just rolls and rolls and rolls across the concrete until it's in the corner and you can't find it anymore. It's because there's almost no friction on point contact to point contact until you start to add loading, and then you deform that, and pretty soon you'll start to see little grooves that come, because whenever you deform something and ask it to roll along, there's a period of its rolling when it goes through the flat section that the velocity here is different than the velocity here is different than the velocity here. Now, if you roll it this way, let's say instead of rolling it back and forth, let's say you roll it longitude into the paper, then you really start to see that the velocity here is different than the velocity here is different than the velocity here. And if you have varying velocities in a bearing, then you automatically have some parts that roll and some parts that slide. So the more you preload a bearing, I guess I'm getting into the weeds, but this is such the basis for everything that you deal with when you start here up to designing a mechanism. When you preload this bearing, you look for something that doesn't slide, that rolls most of the time. So far we have point contact to point contact. We've had point contact to flat. Neither of those are we going to use very often. Okay, what we're going to do, and so this round rail initially got built because the shafting is easy to make. A round straight shaft is fairly easy to make. And this ball bearing, making it roll along there, is fairly easy to make. But as you load it, the change in friction dynamic goes from, as you load this down, it actually changes the friction coefficient. You'd like to think of friction as kind of constant, but in linear bearings, it's not constant. In this type of arrangement, it might start out at 0.0015 with no load, but it probably goes up as high as you'd have to go. It probably goes up as high as 0.010 loaded. It's still rolling. It's still way better than what we had before, which is 0.17. But it's a huge difference, loaded versus unloaded, and that's actually hard to engineer around. When you're expecting it to make a certain movement, whether it's loaded or unloaded, and one time it has a lot of friction, and then the next time you go to move it, it has very little friction, that's tough to program the same thing and have it do something different, right? So this type of bearing is good for light loads, and typically the life of this bearing, it's very load dependent. This bearing block here, the one that this one here, that's this side, this might be good for, let's say, I'll say 50 pounds. You could put on that one, and 50 pounds would be loaded, and 50-pound load always goes with life, right? Those, you got taught that somewhere along the way, that you can't just list the loading, you can't just list the life without mentioning the load. So life, and this might be rated, this might be 0.5 miles, which is an odd term but bearings, linear bearings have to rate the life somehow. And so you say, here's the load, how far will it go before you start to see grooving here, you know, before you start to see little grooves in this spot of the bearing where the bearing touches, and it starts to erode the surface finish, and it's no longer a smooth bearing, and then just when you throw it out. So they have to rate it somehow in distance, because that's what linear bearings do, not rotations. And so it's in kilometers or miles or feet or, you know, something, but it's a long life. And so typically say, oh, that's a half mile at 50 pounds. It might be 500 miles at 5 pounds. It is not a linear relationship, this load and life. You guys had that somewhere. Hopefully you had load and life in 340. Is that where you got? Okay. And did you actually spend some calculations and have to deal?
Yeah, we did a bunch of fatigue life stuff in 340.
Okay. Well, fatigue life's a different thing, right? But similar concept, loading life. So we're looking for bearings in how far they will go under what loads. Similar concept. So the round rail, pretty much they're huge, and they kind of went away because they're pretty simple. You can see in this, you can see here's the, is my camera still on? No. Is the camera still on?
Yeah.
Yeah.
Yep.
Okay, so you can see in here the multiple grooves, the loading zone. Here's you can see the bearings, little ball bearings moving in there. They're coming in and out of the loading zone. Some of these will go all the way around. Some of them go part way around. All the way around would get rid of any deflection that you would have this way. This one is plastic, cheap. This one's metal. So there's all sorts of different varieties. You know, the catalog's this thick on round rail bearings, but those catalogs are also not used anymore. So we moved on, and we went to what would be called, we went from round rails to linear guides. And this is what we use today. And here's why. You're looking for something that can handle if we go back to our little ball bearing, we don't want to run it on this point contact to point contact. That's bad. We don't want to run it on flat. That's not that good either. That doesn't handle much load. We want to run it in a groove, and you'd like to have, so there's two types of grooves that you would run this in. One is called Gothic arch, and it's all about the velocity and the loading zone. You guys don't cover this in 340, right? I presume the actual how bearing rolls. We got to cover it here because everything you do in selection relies on this little mechanism. So Gothic arch, they would actually, if this were the groove part of it, they would have a contact patch here and here, and then it would do this kind of thing. It would come away and then away. So you'd have two spots where you had forces on here. And what you're trying to do is get the zone from here to roughly be the same velocity as here to here, so that it really kind of has two rolling spots to it. It rolls down a groove. It doesn't, you wouldn't want the groove to be, you wouldn't want it to be this. Let me draw this. This would be bad. Right? That's bad. That's point contact to line, but at least there's two lines now. But so what you do is you start to machine in this groove right here and along that side. So turns out that's pretty easy to make. Lots of most ball screws use a Gothic arch approach. THK came along. This was everybody. And when I mean everybody, here's there's SKF, there's NSK, there's IKO, there's, let's see, who are some, oh, there's Hywen, who broke the mold. I don't know what they were thinking. You're supposed to, little bearing companies, I thought, were supposed to be all 3 letters for some reason, because they always are. But Hywen, and then THK came along and they said, no, we don't like that. We're going to manufacture something that looks like this. Here's the ball, and we're going to go with something called radius groove. And so what they did is they made the radius groove. If this is your outside part, they said, so again, it's all about making the velocity rolling, not sliding anywhere. And they were able to come along and put in a groove here in the bottom like this. And this groove was like, if this is R, then this, excuse me, let me do it this way. This was R, we'll call it RX, and we'll call this R, and RX was 1.01 times R. And so they made a very precision groove that would give you a loading zone, not on the sides, but it would give you an equal loading zone through here when you gave it a certain load. And the result of this was the coefficient of friction of this was 0.002 to 0.003 from no load to full load. This one, coefficient of friction, would start out at 0.002 and go up to about 0.0007. Now this sounds like stupid little numbers, right? But when you design a certain preload and you know that basically the friction never changes under load, that's a huge deal to your programming and to your being able to build a machine that can make motions and is accurate. So THK came along, and that's all we ever used in our machines because it was so superior. But you paid for it, but you could get accuracy. These manufacturers, they would all come visit us, and they would tell us how their bearings were so good, and we'd just simply, we'd say, okay, tell me when you solve that, because that's the key to motion control. And they're like, yeah, well, the salesman come along, whatever. All of a sudden, about 10 years ago, THK's patent wore out. And now nobody does that hardly anymore. Only the cheap companies do Gothic arch. This radius groove is now pretty much the standard, and they all shifted over. And the hard part about this is that this groove, this is meters. I don't know why all of a sudden I think in feet, and all of a sudden I start talking about Japanese bearing manufacturers, and I have to switch over to the metric system for some reason, because that's how. But they're trying to manufacture. The hard thing about the radius groove was manufacturing this groove not in one little spot, but manufacturing it over a 2-meter rail. That was the tricky part. And the way they did it is they, just like how they pick precision resistors, is you make the best machine you can, and then you make parts on it, and then you take the parts off that machine, put them in the machine, and make more parts. And those parts are better because you took the very best bearings that you made, the linear bearings, and you put those in the machine that was making linear bearings and made more linear bearings. And you do that several iterations, and pretty soon you get to really good flatness, and the groove then was very controlled and didn't undulate. And that was their key to being able to make these radius groove bearings. The outline of this bearing is, sometimes we call them square rail bearings instead of linear guides. But essentially it started out like that. And then what they would do, they would put in a little bit of groove here, a little groove there, a little groove there, and a little groove there. And that's where the balls would roll. So one of the things that happens then is as soon as you put balls on opposing surfaces, you get a force here and here and a little bit to the side, but then you also get one here and here. So now you begin to be able to handle moments. You'd be able to get, this would be, back to that very first conversation we had, this would be the side load to the bearing. This would be the, I don't know, top load. You know, there's not an absolute name for it, but the key is that you can also have, like, this would be a roll moment around this, because these handle multiple directions. So you put in multiple grooves, and I won't take this one apart, but this one has 1, 2, 3, 4 channels of little balls inside of it. So, and I have some, like, here's one. This would be a size 25 bearing. So just as a reference, here's 2 bearings similar size. Here's the square rail or the linear guide. This is an old THK one. This is an SR something, probably an SR 25, because this is 1 inch. And here is the round rail. This handled 50 pounds because it was point contact to point contact of the ball bearing on the round steel rail. This one is radius groove. This one's probably about 3,000 pounds and still has a coefficient of friction of 0.003. It's basically as close as you get to bearing perfection as there is the linear guide. And then so you buy these, and when you go to buy a linear guide, you're going to ask for various precision levels. Just like if you're buying resistors, you can buy 10%, 5%, 1%. Well, this case there, I think it's C7, C5, C3, you know, there's, I don't know why they call it C, but there's various precision levels. And they don't actually give you accuracy. What these give you is called, they give you what's called straight line accuracy. What straight line accuracy means is if you put the bearing block over the top of this and then ask it to go in a line, so let's just make the line of this bearing block goes in a line, and this green also has a line. And the straight line accuracy then tells you as one goes throughout the length of travel, if you put, for instance, a laser beam on top of the bearing block and pointed it at the wall, you know, if this is our laser, and we pointed it, we'll make the laser light, we pointed it over here at the wall, how much does it dance around on the wall? Right, it's going to go up and down and make a pattern on the wall. As this goes through its travel and this goes through its travel, you end up with a straight line accuracy. And that's what they give you on these bearings. They don't really tell you an accuracy per se, but they tell you once you install it, what you can expect to have happen between the block and the rail. So your real challenge with any of these bearing blocks, once you buy the precision once you buy the precision level that you want, the actual challenge is not ruining it, not ruining your accuracy. How do you ruin the accuracy? Well, let me just draw something. Let's say I took this fabulous bearing and I mounted it on a piece of sheet metal. Or I mounted on, worse yet, or maybe one worse. I mount it on a piece of aluminum extrusion. So I mount this fabulous bearing that has these two perfectly collinear rail and bearing block along its whole travel. I bought this precision grade, and then I mount it to an aluminum extrusion, which has, pretty much as I've shown it. So the question then is, the question you have to ask is, what wins? And by what wins, I'm talking about the deflection when you bolt them together. So you squeeze the rail and you squeeze the aluminum extrusion, you mount it together. There's little bolt holes in here that you bolt this down, and it goes down into the material. This is a little set screw kind of thing. So this gets bolted down into something, and our here's our something that we're bolting to. What wins the deflection? As you begin to cinch these bolts down, you're changing the shape of one or the other. They both have their own flatness. So this one, the bearing itself, doesn't tell you a flatness. It only tells you straight line accuracy, which means it's up to you to pick a surface to mount it to, which is flat, which aluminum extrusion, no flatness. You ruined your bearing if you mount it to that. Instead, you go buy a machined surface if you want true flatness, or you go out and you get a piece of metal and you machine it as best as you're willing to pay on a CNC to have a machined surface, and you mount it to machined surface. We've had projects at the Mechatronics Center. We did a machine where we calculated out where we needed that point in 3D space to be. And as we worked backwards towards the bearings, we realized the flatness had to be beyond anything that could be done in Chico. And we actually found a company, is it Paradise? Or there's a couple there's one in Sacramento, one in the Bay Area, that had a machine tool that was capable of making a flat enough surface that when we mounted our bearing down to it, when we secured it down, it actually got flatter. So making precision bearings is all about the flatness, because remember, you're trying to get, back to this, you have all these things that have to happen, and what you're trying to get is this point here to move along a line in 3D space. You're not trying to get it to do this and up and down or side to side. When you tell it to move, you're trying to tell it to move in a line, and that's the 3D accuracy of your machine. So what I want you to do, I'm going to stop and we're going to go back to lab here in a minute. What I want you to do is, there's a document on the California Mechatronics website. The document is called Quantifying Precision Mechanics, and it kind of runs through the different levels of, or different terms: resolution, precision, repeatability, accuracy, straight line accuracy, positional accuracy, kind of in general what those things mean. But it all has back to, what are the surfaces, how do they made up, and then how do things travel along those surfaces. So that's kind of what we're trying to get to.